Yesterday we were finishing up talking about, well, not finishing up, but we were talking about power series. And we're going to continue talking about power series. And we were looking at how on certain intervals, the series itself was basically exactly the same as the function that we were looking at that it was representing. And we're going to try and just do a few more practice problems with manipulating that 1 over 1 minus x term to turn into other series that we can use to represent other functions, like, for example, 1 over 1 minus 2x. So we want 1 over 1 minus 2x on the interval from -1/2 to 1/2. So what should that series look like? Should just be a sum from n equals 0 to infinity. And now instead of having a 1 minus x, we have a 1 minus 2x. So it ought to be 2x to the n. And traditionally, we would write this as 2 to the n, x to the n, normally. And that series, what's the first term of that series? If I plug in n equals 0, the first term should be should be 1, good, and the second term should be wonderful, 2x, and the next term should be what, 4x squared, and the next term should be 8x cubed, and so on, right? And just to show that the interval of convergence is -1/2 to 1/2, we need to think about what is our r value. What is the common ratio between the terms of this geometric series? Well, it's 2x. Each time I'm multiplying the previous term by 2x. And so, as we knew for any geometric series, the common ratio needed to be less than 1 for the series to converge. So that would tell us that x is less than 1/2, greater than -1/2. So this one is only valid for that 1 unit of length between -1/2 and 1/2. Good or no? Wonderful. All right, let's do another one. Let's see if we can find a power series representation of 1 over x that would be valid on 0 to 2. So what we first want to do is see if we can find a way to rewrite 1 over x as 1 over 1 minus something. And then all we'll need to do is put in that something into our series as the x. Instead of x to the n, we'll have something else to the n, whatever's inside these parentheses. So what term could I put in here? 1 minus x will do it. Thank you, Noah. So this should then be the same as the sum from n equals 0 to infinity of 1 minus x to the n, with a common ratio of 1 minus x, which would mean that we would put the absolute value of 1 minus x less than 1, or 1 minus x is less than 1 greater than -1. We'd subtract the 1, and then we'd multiply by a -1, which would flip our inequality signs, and we get x is greater than 0, less than 2, which is exactly what we wanted. And just for the fun of it, let's just look at this one on Desmos. So we know 1 over x looks like this. And if we have the summation from n equals 0 to, let's say, 50 of 1 minus x to the n, our hope is that that should match up between 0 and 2. So we'll give it a second to slowly do its calculation. Then we can see that from 0 to 2, even with just the 50 terms, matches up really, really well. Okay? So we can see that that interval of convergence may change, but we can still see it always will converge on that interval. What was the one we did just before this one? We did 1 over 1 minus 2x, right? I believe. And for this one, you can see, we said that it would only converge from -0.5 to +0.5, so it should only be good on the interval from -0.5 to +0.5, and we can see that that is once again the case. Everybody good there? We all doing okay with these? Wonderful. Okay. Cool. Let's find a power series to represent 1 over 3x and see if we can find the interval of convergence for it. So I'm going to give you guys a couple minutes here to work on this one on your own. See if you guys can come up with a series to represent 1 over 3x and find the interval of convergence for your series. Ready, go. I forgot to start recording. So we wrote 1 over 1 minus 3x, which became the sum from n equals 0 to infinity of 1 minus 3x to the n. And then we set the absolute value of that common ratio less than 1 to find our interval of convergence. So 1 minus 3x less than 1 greater than -1. -2 is less than, -3x is less than 0, and then x is less than 2/3 but greater than 0. Is that you all got? Any questions or issues with that? All right, we should also be able to go in the opposite direction. So I should be able to give you a series and say, find the interval of convergence of this geometric series, and then find a function of x that represents that series. So this first one is one we already did, right? We know that this is the sum from n equals 0 to infinity of 2x to the n. That's the one we were just looking at, right? So it just becomes 1 over 1 minus 2x. We already did that one earlier, right? Just going from this to this. And we knew that the interval of convergence was x is less than a half greater than -0.5. But what about this one? I can figure out what the common ratio is by just multiplying everything that's being raised to some sort of power of n. So -1/2 times x minus 3 ought to be 3 minus x over 2, right? And so that's our common ratio. This series is the sum from n equals 0 to infinity of 3 minus x over 2 to the power of n. And if we want to figure out what series is represented, or what function is representative of this series, we'll do 1, because that's our first term. If n is 0, this is all just 1. And then over 1 minus the quantity 3 minus x over 2. And so we should be able to take this and put it into a nice, simpler form. We get a common denominator, multiplied by 2 over 2. So then we've got 2 minus 3, which should be a -1, and we've got a negative x. So this ought to be 1 over x minus 1 over 2, which would be 2 over x minus 1. Everybody good with that? Cool. And then we'll need to put the absolute value of 3 minus x over 2 inside of an absolute value and set it less than 1, which will, if we multiply by 2 and clear out all that absolute value, is going to give us -2 is less than 3 minus x is less than 2. And we should be able to subtract the 3. -5 is less than -x is less than -1. And x is greater than 1 but less than 5. So this particular series has an interval of convergence of 1 to 5, and it should represent the function 2 over x minus 1. Does that make sense to everybody? So there's 2 over x minus 1. And our summation was the sum from n equals 0 to infinity, we'll say 50. And what was it? It was 3 minus x over 2. All being raised to the power of n. And so we should see that this should converge between 1 and 5. And that's exactly what it does. Everybody see that? Everybody feel pretty good about that? All right. So next thing we're going to do, we still got like 20 minutes. That's good. Next thing we're going to do is we're going to take a look at a series for 1 over 1 minus x squared. So we want to see if we can use the series, the power series for 1 over 1 minus x to come up with a series for 1 over 1 minus x to the second power. Any thoughts on how we might go about doing that? All right, so we got people saying 1 minus x squared. We could set 1 minus x squared equal to 1. Yeah, so I mean, we could do that. That's what we've been doing. But I want to see if we can find a different way to figure that out. We should be able to come up with a different way. And I mean, you guys are right. We could come up with a series that works out like that. But we should be able to come up with something even cooler and even better. Let's think for a second. Let's think about what class are we currently taking? What class is this? This is an easy question. What class are we currently taking?
Calculus BC.
Calculus. All right, so when we talk about calculus, we normally talk about limits and we talk about derivatives and we talk about integrals. That's what you do in calculus, right? That's calculus. True? Yeah. All of this series stuff that we've done so far doesn't really involve much calculus, does it? It hasn't so far. Let's see if we can find a way to incorporate one of those things into this problem. All right. Yes, let's take the derivative of 1 over 1 minus x. What is the derivative of 1 over 1 minus x? It should be, according to the reciprocal rule, the opposite of the derivative of the denominator over the denominator squared, which just so happens to be the exact same function that we were looking at up here that we wanted to find a power series to represent. So the very cool thing that we can do with any power series is we can take it and we can just take its derivative and end up with a new series that represents the derivative of our original function. So what is this series? This series is the sum from n equals 0 to infinity of x to the n. So we took the derivative of 1 over 1 minus x. Well, let's take the derivative of this series. And the derivative of that series should just be the derivative of x to the n, which should be what? The sum from n equals, well, we'll worry about n equals what to infinity in a second. But what's the derivative of x to the n?
nx n minus 1.
Yeah, nx n minus 1, exactly. Hold on 1 second. Okay, sorry about that. Okay. So, sorry, my kid's got his laptop sitting next to mine, and for some reason his Zoom meeting restarted or something. So we end up with this summation from n equals now 1 to infinity of nx to the n minus 1. And this is something you'll want to note, that anytime you start at n equals 0 and you take the derivative of something to the power of n, you're going to have to raise that index up to an n equals 1. And so what does this series then look like? If I were to plug in values of n equaling 1 to this, what do we get? If n equals 1, what do you get? It should get 1. What if n equals 2? Should get 2x. What if n equals 3? Should get 3x squared, and we should get 4x cubed, and so on, right? If we plug those values in. Now, what if we were just to take this and term by term differentiate it? What's the derivative of 1? 0, right? Derivative of x is 1. Derivative of x squared is 2x. Derivative of x cubed is 3x squared, and so on. Good or no? Now, what is the interval of convergence? Well, when you take a series and take its term-by-term derivatives of it, then all that happens is you end up with the exact same interval of convergence. So this series should converge on -1 to 1 as well. So let's go in and take a look. We have 1 over 1 minus x to the second. And we have the sum from n equals, we'll say 0 to 50 again. Actually, we'll say n equals 1 to 50. And we are going to do nx to the n minus 1. And we should see that between -1 and 1, I know it doesn't look right yet, but it just was calculating before I finished typing that, I think. There we go. Nx to the n minus 1 should look pretty darn good for -1 to 1 still. So it has worked out. Good or no? Everybody good with that or no?
Good.
Great. So a very important concept, that you can take the derivative term by term of any power series to get a new series, a new power series to represent the derivative of the original function. And that's effectively all that I've got written here. You can do it centered around 0. You can do it centered around any a value that you want. And the new series will always converge on the exact same interval as the old series. Good or no? I'm assuming a few people probably want to write that down, so I'll give you guys a couple of seconds here to write that down. So somebody was asking if the interval of convergence is the same as the radius of convergence. No, so we haven't really started talking exactly about what a radius of convergence is. The radius of convergence is just is half the length of the interval of convergence. It is, yeah, I mean, it's half the length of the interval. So that's what the radius of convergence is. All right, everybody good there? Should we move forward and try and do another one of these? Most of what we've done so far should be pretty, I hope, pretty straightforward. The further we get into this unit, the first couple of days of this unit are pretty easy, but then it starts to become a little more difficult. So hopefully you're all hanging in there at this point. So we've used this one before, right? This one is 2 to the n, x to the n. This is, or 2x to the n. This was the series for 1 over what? 1 over 1 minus 2x, right? We already dealt with that one. Kevin, higher powers of 1 over 1 minus x, probably not. Not exactly. We will deal with writing. I mean, we'll have to be able to. You just mean like finding a series for powers higher than 1 over 1 minus x, like 1 minus x to the 4th or something like that. Yeah. No, I wouldn't expect them to ask you that on the AP test. I won't require you to do that either. All right, so we have the function 1 over 1 minus 2x here, which is 2 to the n, x to the n. We want to find a power series for f prime of x. Well, first off, what is f prime of x? F prime of x ought to be the opposite of the derivative of the denominator over 1 minus 2x squared. So we're looking for a series that represents 2 over 1 minus 2x squared. And all we have to do is take a derivative, raise our index up by 1. Let's see, what's the derivative of 2 to the n, x to the n? Two to the n is just a constant, right? So the 2 to the n can just stay. So we have 2 to the n, and then the derivative of the x to the n is just nx to the n minus 1. That ought to be a perfectly good power series to represent 2 over 1 minus 2x squared. Good or no? So far good? What if we wanted to rewrite this so that we could figure out and show what the interval of convergence is? And we know what the interval of convergence should be. What was the interval of convergence for the other one? Should still be negative 1/2 to 1/2. But one thing we want to be able to do is we also want to be able to rewrite this. Well, actually, this is perfectly fine. Never mind. I don't need you to rewrite this. This is good. Everybody good there? Thinking I'd have you rewrite it in a different way, but we don't need to. All right, let's take a look at this one. This is another one we dealt with, 1 over 1 plus x. We've used this one, right? It's 1 minus x plus x squared minus x cubed and so on. Can we find a power series to represent the natural log of 1 plus x? And the answer here should be yes, as more people are leaving the class. More people don't care about my class anymore. That's fine. What should we do? Any thoughts? Yeah, good. Now this one we're going to need to integrate, right? The integral of 1 over 1 plus x is natural log of 1 plus x. So what we're going to do is we're going to say that the natural log of 1 plus x is equal to the integral, and I'm going to choose to do this from 0 to x of 1 over 1 plus t dt, making it a definite integral with the lower limit equaling 0, because that way I know what the integral of this is, right? The integral of this should be the natural log of 1 plus x minus the natural log of 1 plus 0. And that 1 plus 0 there is, natural log of 1 plus 0 is natural log of 1, which is 0. So this should just give me natural log of 1 plus x. Because every time we integrate something, we end up with a constant if we don't use a definite integral. So if we have a definite integral, we can put a lower limit in for our definite integral that gives us a nice easy value here. We can just do that. If not, if we can't find a nice easy lower limit, we're going to have to do it as an indefinite integral and solve for a constant. We'll worry about that later. But right here, if I make my lower limit 0, then the integral of 1 over 1 plus t from 0 to x is this function. This function's integral, which is natural log of 1 plus x minus natural log of 1 plus 0. Okay, good. So what we'll do then is we will take this series, the sum from n equals 0 to infinity of negative 1 to the n, x to the n, and we'll just integrate it. So we're going to integrate this from 0 to x. And what does that give us if we integrate that? Should give us negative 1 to the n is just a constant, right? That should just stay. How do you integrate x to the n? It becomes x to the n plus 1 over n plus 1. And so this series should represent the natural log of 1 plus x. And we will say that this is valid also for negative 1 to 1. And I've left this giant gap here. When you integrate, it is good for at least the same interval. But what we will eventually need to learn to do is to check the endpoints. It's not something we're going to really be able to do super well at this exact moment, but we're going to try to at this function in the last 5 minutes or so here. But whenever you integrate a function to find a new power series, the new series is valid, or it converges for at least the same interval, and it might converge at the endpoints as well. All right, so that's an important point for us to note. So let's think about this. One way we could check the endpoints is by just plugging in negative 1 and 1 in here. So if I plug in negative 1 to natural log of 1 plus x, that's the natural log of 0. Does that exist? Does the natural log of 0 exist? No, it does not. So therefore, it's certainly not going to converge at negative 1 because our function doesn't even have a value at negative 1. But what about at 1? at x equals 1, we're looking at a sum from, that's not the sum from n equals 0 to infinity of, and what is our series? It should be -1 to the n, x to the n plus 1. So if we're talking about when x is 1, instead of writing x to the n plus 1, we should just write 1 to the n plus 1. And the denominator is just n plus 1. The question is, does that converge? Does this series, our series for natural log of 1 plus x that we just wrote, when evaluated at x equals 1, equal the natural log of x plus 1? Natural log of 1 plus 1. Does it equal natural log of 2? That's the question that we're trying to ask ourselves here. And we don't have a good way to prove this yet, but we could, by just using a calculator, see if it's true. What's the natural log of 2? There it is. There's the natural log of 2. And here's my sum from n equals 0. We'll put in a value in a second. If we have -1 to the n, and then we have 1 to the n plus 1. Well, what's 1 to the n plus 1? Does it matter what n is? No matter what n is, 1 to the n plus 1 is just 1. So we don't need to put that in. And then it's over n plus 1. So let's just say, okay, what if I go from n equals 0 to n equals 5? That's 0.6166666. That's fairly close to 0.69. What if I make it n equals 10? It's gone a little bit above. 15 back below, right? But it's 0.66, which is closer than it was before. What if I make it 25.67? That's pretty good. What if I go to 250? 0.695. What if I make it 2,500? 0.6933. 0.693167. That's getting pretty close, right? The further out I put values in here, it sure does look like it is converging towards that value of the natural log of 2, doesn't it? Wouldn't you guys agree with that? Now, obviously, this is not an exact way to figure this out. We really do need some other rules to figure it out. We'll have a rule to prove why this is true. But we can, I can tell you that it does converge at x equals 1. And you will want to also memorize this series, that the sum from n equals 0 to infinity of -1 to the n, -1 to the n, x to the n plus 1 over n plus 1 equals the natural log of 1 plus x for -1 to 1, inclusive on the 1, but not on the -1. So this, I know I told you to memorize the one for 1 over 1 minus x. Well, memorize the one for natural log of 1 plus x also. That's the second one you're going to need to just sort of know. Good or not good? Okay. And I'll leave this up for a couple minutes here into the passing period. We're going to be done here at this point. We'll do some more with the integration tomorrow, or Monday, I guess. But I'll post this page up in the notes also for those of you that want to write it down. This is just sort of the generic formula. And just integrate term by term, and you'll see that you get each of the same, you get each of those, each of those values that you should get if you were to, I guess we didn't really show it with this one. So we could really quickly do that. If I term by term integrate this, what's the integral of 1? X, right? Minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 and so on. And if I write out the values of this starting at n equals 0, well, at n equals 0, this thing comes out to be 1 times x over 1, so that's x. And n equals 1, we're going to end up with minus, from the alternating part of it, x squared over 2. And then the next one will be a plus because it's -1 squared, and it'll be x cubed over 3, and so on. And we see that those terms come out the same if you plug into the series or if you term by term integrate. Does that make sense?